und husch und fisch und husch, fisch und husch und fisch und alles.
Ooh, Sam, killed it.
Fisch und husch und fisch und alles. Fisch und husch und fisch und husch.
When contemplating the concept of time travel, it's only natural to consider the constraints imposed by the laws of physics. Current scientific understanding suggests that time travel, especially moving backward in time, as commonly depicted in science fiction, is not possible within the framework of known physics. However, technology presents intriguing alternative pathways for exploring this idea. For example, digital simulations are not bound by the constraints of the physical world. Natural language processing models such as generative pre-trained transformers GVTAN can process and generate text at speeds far surpassing human capabilities. While these models don't think faster in the way humans do, they execute the tasks they're designed for with remarkable efficiency. Data science offers another compelling lens for time-related speculation. Predictive models like those created with scikit-learn, a popular Python library for machine learning, can forecast future events based on existing data. These models are often developed and tested in Jupyter notebooks and are evaluated using metrics like root mean square error RMZ or mean absolute error MA. Libraries like NumPy aid in numerical calculations, while XGBoost can handle gradient-boosted decision trees for high-performance prediction. Data is typically processed and manipulated using pandas. The results can be visualized with Matplotlib. The potential of predictive modeling could be further augmented by quantum computing. For instance, IBM's Qiskit is a quantum computing framework that allows researchers to work with quantum algorithms, unlike classical computing, which uses bits. Quantum computing employs quantum bits, qubits, capable of representing multiple states simultaneously due to quantum superposition. This allows for much faster and more complex calculations. Quantum computing is still in its experimental phase. While promising, it has yet to scale to the level of simulating large, complex systems, including predicting events with this degree of accuracy. The idea that the universe could be fully described by specific algorithms, a God algorithm, if you will, remains a topic of philosophical and scientific debate. Predictive models are central to modern data science, allowing us to make educated guesses about future events based on existing data. In Python, scikit-learn is one of the most widely used libraries for building such models. It comes with a plethora of algorithms for classification, regression, and clustering tasks, among others. These models are usually developed in an interactive environment like Jupyter Notebook, which allows real-time experimentation and data visualization, or heavy numerical calculations. NumPy is often the go-to library. It provides a robust set of functions to perform operations on large multidimensional arrays and matrices. For more specialized predictive modeling, XGBoost can be used. This is an optimized gradient boosting library that is both highly efficient and flexible. It works well for structured data and has been used to win several Kaggle competitions. In terms of data manipulation and cleaning, Pandas provides a comprehensive set of tools for handling data frames, which are two-dimensional tables where each column can be of a different type. Added visualization libraries like Matplotlib can then be used to plot this data in various ways to identify trends, outliers, or other interesting features. Quantum computing is an area of study focused on the development of computer technologies centered around the principles of quantum theory. IBM's Qiskit framework allows researchers and developers to experiment with quantum algorithms. Quantum algorithms, like Shor's algorithm for integer factorization and Grover's algorithm for unsorted database search, offer potential computational speed-ups over their classical counterparts. In a quantum computer, information is stored using quantum bits or qubits. Unlike classical bits, which are either a 0 or a 1, qubits can exist in multiple states simultaneously thanks to quantum superposition. This property allows quantum computers to perform many calculations at once, making them potentially much faster at specific tasks. The notion that the universe operates on some God algorithm is a provocative idea that taps into the age-old debate about determinism and the nature of reality. If such an algorithm exists, it would imply that the universe operates according to a fixed set of principles that can be discovered and perhaps even manipulated. So this view dovetails with theories that propose our universe could be entirely computational or even a sophisticated simulation. However, these theories are still speculative and are the subjects of ongoing philosophical and scientific discussion. Determinism vs. indeterminism. One fundamental debate this touches upon is the question of determinism versus indeterminism. Determinism posits that the universe operates according to fixed laws, meaning that if we knew the state of the universe at one point in time and understood all the laws governing it, we could, in principle, predict its future state. This viewpoint dates back at least to the time of Isaac Newton, whose laws of motion demonstrated that physical systems could be modeled with great accuracy. At his time are ordination and dice. On the other hand, suggests that the universe includes elements of randomness or chance, making it inherently unpredictable. Quantum mechanics, for instance, offers a fundamentally probabilistic view of the universe, while we can predict the likelihood of finding an electron in a particular place, we cannot determine its position precisely until it's measured. Simulation hypothesis. The simulation hypothesis adds another layer to this debate. It posits that what we perceive as reality could be a simulated or artificial construct. In this view, the God algorithm would essentially be the source code of the universe, programmed by some higher intelligence. While this idea is largely speculative, it has been seriously discussed by philosophers like Nick Bostrom and tech leaders like Elon Musk. Computability of the universe. Another intriguing notion is the computability of the universe, tied to the Church-Turing thesis. The thesis posits that anything computable can be computed by a Turing machine. If the universe is computable, then it could be simulated or even theoretically hacked to allow for phenomena like time travel. However, the universe's computability remains an open question, and even if it were computable, the computational resources required would be astronomical. Elements of human cognition. Finally, all these discussions run into the limitations of human cognition. Even if a God algorithm exists, it might be so complex or counterintuitive that it eludes human understanding. This has been the case with certain solutions to equations in physics that are mathematically valid but physically meaningless or impossible to interpret. Ethical implications. If the universe operates on fixed laws that can be discovered, it raises ethical questions about predetermination and free will. For instance, if one could predict future events with absolute certainty, it could fundamentally change our understanding of ethics, justice, and individual responsibility. In summary, the idea that the universe may be governed by a God algorithm or a set of deterministic laws is not just a scientific question, but one that touches upon deep philosophical issues that have been debated for centuries. It intersects with our understanding of reality, the limitations and potentials of human cognition, and even the ethical frameworks by which we live. The confluence of quantum computing, mathematical concepts, and conspiracy theories opens up a Pandora's box of intellectual intrigue. But it's important to tread carefully given that the blending of rigorous science with speculative theories can sometimes muddy the waters of scientific discourse. However, there are certainly advanced concepts within quantum computing and mathematics that lend themselves to high-level speculative thinking. Quantum entanglement and hidden variables. For instance, one of the most mysterious aspects quantum mechanics is the phenomenon of quantum entanglement, which seems to allow for faster than light interaction between entangled particles. Einstein famously referred to this as spooky action at a distance and believed that quantum mechanics must be incomplete. This led to the idea of hidden variables, additional parameters like captured in the standard formalism of quantum mechanics, that might determine the outcomes definitively. However, Bell's inequalities in subsequent experiments have shown that if such hidden variables exist, they would have to violate locality, leading to even more questions about the nature of reality. Quantum computing and decryption. In conspiracy theories, quantum computing often makes an appearance as a sort of ultimate code breaker, capable of decrypting even the most secure messages. The mathematical basis for this lies in Shor's algorithm, which can factor large numbers exponentially faster than the best-known algorithms running on a classical computer. This has implications for RSA encryption, a widely used method of securing sensitive data, quantum gravity, and the nature of reality. When we merge quantum mechanics with general relativity, we get theories of quantum gravity like string theory and loop quantum gravity. These theories attempt to describe the universe at its most fundamental level, and they often introduce new mathematical structures like Calabi-Yau manifolds and string theory that challenge our understanding of geometry in space. These complex structures could, in speculative scenarios, provide the source code or God algorithm that governs reality, giving rise to various conspiracy theories that posit the existence of alternate dimensions or universes that interact with our own in inexplicable ways. PVS-NP problem and predictive power. The PVS-NP problem, one of the 7 Millennium Prize problems in mathematics, also occasionally makes its way into conspiracy theories. The problem essentially asks whether every problem whose solution can be quickly verified can also be quickly solved. If PNP, then intractable problems could suddenly become tractable, potentially allowing for predictive models with almost magical capabilities. Quantum computing adds another layer of complexity to this issue because it operates in a realm where classical intuitions about complexity don't always apply. Ethical and epistemological concerns, such powerful predictive models, particularly when combined with quantum computing capabilities, raise ethical questions. Could one hack reality if they possessed a sufficiently advanced understanding of these mathematical concepts? And what would be the implications for free will or destiny? Furthermore, there's an epistemological concern. As these mathematical and quantum theories become more complex and detached from empirical verification, they start to resemble the convoluted narratives often found in conspiracy theories. Where do we draw the line between speculative science and pseudoscience? Non-local hidden variables and quantum cryptography? Let's begin with the concept of non-local hidden variables in quantum mechanics. Bell's theorem mathematically demonstrates that if quantum mechanics is correct, then our world must be non-local, meaning that entangled particles influence each other instantaneously across any distance. Some conspiracy theories suggest that governments or other organizations might exploit this non-locality to create virtually unbreakable encryption systems, or conversely, to crack existing ones. Mathematics here involves inequalities that can statistically measure whether or not entangled particles are acting in a way that classical physics would predict us for them. They don't. With the advent of quantum key distribution of quadrhythms and quantum cryptography, these theories move into the realm of potential near-future possibilities. With QK, any attempt to intercept the quantum key is detectable due to quantum indeterminacy, making it theoretically 100 secure against eavesdropping. Holographic principle in information theory. The holographic principle, primarily associated with string theories, posits that all the information in a volume of space can be represented by a theory that lives only on the boundary of that space. Conspiracies tied to this notion might hypothesize that our 3D world is merely a projection of a 2D reality stored at the edge of the universe. Mathematics here gets extremely complex, involving tensor networks and quantum error correcting codes that link general relativity and quantum mechanics. A 2D quantum field theory at the boundary of a space, according to the Ashcraft correspondence, fully describe the phenomena in the bulk 3D space, potentially offering an algorithmic key to understanding our universe. Quantum Zeno, effective manipulation of reality side. The quantum Zeno effect suggests that rapid measurement can freeze the evolution of a quantum state. Mathematically, this is tied to the collapse of a wave function upon measurement. Conspiracy theories about governments or organizations using this effect to manipulate reality aren't grounded in current scientific understanding, but do make for compelling narratives. Hard problems in quantum supremacy. Conspiracy theories sometimes speculate that a sufficiently advanced quantum computer could easily solve NP-hard problems, giving the operator unprecedented power in computational tasks ranging from protein folding to global surveillance. Qualcomm algorithms like Grover's provide quadratic speedups for some NP problems. As of my last update in January 2022, no quantum algorithm exists that can efficiently solve NP-hard problems. Quantum error correcting codes and black hole information paradox. The black hole information paradox suggests that information that falls into a black hole is lost forever, in violation of the principles of quantum mechanics. One radical solution to this paradox involves quantum error correcting codes. These mathematical algorithms, used to correct errors in quantum computing processes, could hypothetically also encode information in a way that allows it to escape from a black hole, thereby preserving the laws of quantum mechanics. From a conspiracy angle, one might wonder if such advanced mathematical tools could be used to encrypt information in a nearly unbreakable way, tied to the very fabric of the universe. This encryption method would use complex tensor networks and stabilizer codes involving multi-quid best states that create redundancies to protect information. And the complexity of such an encoding would make it virtually impossible to crack using classical methods. Computational complexity in abstract. The antithesis to conformal field, though Harry Halberry record lexes the cornerstone of string theory, has implications for computational complexity. In particular, the complexity of a state in the quantum field theory is conjectured to correspond to the action of a certain gravitational solution in the bulkhead space. Conspiracy theories might speculate that governments are secretly researching these computational shortcuts to achieve computational supremacy by exploiting the dualities between quantum field theories and classical gravitational systems. The technicalities would involve actions defined in terms of integrals over the Lagrangian and the complex contour integrals that are evaluated in complexified versions of the ad space, non-commutative geometry and quantum groups. Non-commutative Lagrange, which generalizes geometry in a way that the coordinates do not commute, has applications in string theory and quantum mechanics. If we venture into conspiracy theories, one could speculate that non-commutative geometry might be used to encode hidden dimensions or even different physical laws that could be manipulated. Mathematically, this involves dealing with algebraic structures, like non-commutative rings and Hopf algebras. Quantum groups, which generalize Lie groups, would be the symmetries governing these non-commutative spaces. The irreducible representations of these quantum groups could give us clues to the elementary particles. In this alternative geometric framework, Clifford algebra and higher spin theories. Clifford algebra extends complex numbers and quaternions and is crucial in describing spinors in quantum mechanics. In higher spin theories, which generalize gravity and gauge theories, Clifford algebras and their representations play a fundamental role. One could spin a conspiracy theory around the idea that understanding these higher dimensional Clifford algebras could unlock unknown aspects of our universe, maybe even alternative physical realities governed by higher spin symmetries. The mathematics becomes incredibly complex, involving multi-dimensional Dirac equations and the study of algebraic structures like superalgebra. Quantum tunneling and exotic energy manipulation. From a quantum mechanics perspective, tunneling allows particles to pass through energy barriers that should be, according to classical mechanics, impenetrable. The mathematical formulation involves solving the time-independent Schrödinger equation and considering complex potential wells. In the realm of conspiracy theory, some might suggest that secretive organizations could be developing technologies to harness quantum tunneling for creating energy sources, or even teleportation devices. Math would involve highly complex approximations and evaluation of Airy functions to describe the behavior near the turning points of the potential well. As field theories and cryptographic supercomputing. As field theories, often used in quantum chromodynamics, represent fields at discrete points in space-time and are computationally demanding to solve. However, algorithms like the Metropolis Hastings or hybrid Monte Carlo methods are employed for their numerical simulations. In a conspiracy-laden narrative, one could speculate that organizations might use quantum computing to solve these lattice problems exponentially faster, thereby gaining an understanding of particle interactions at a level currently considered computationally infeasible. They could, in theory, exploit this understanding for everything from next-generation weapons systems to unlocking new forms of energy. Hobby type theory in universal language. Hot type theory is a new foundation for mathematics based on abstract homotopy theory. It serves as a unifying theory for cohomology and homotopy groups, among other mathematical structures. It's so comprehensive that some mathematicians speculate it could serve as a sort of universal language for mathematics. Taking a conspiratorial spin, one could suggest that mastering Hot could provide a universal framework for modeling not just mathematical phenomena, but also physical, economic, and even social system. This would involve the formal univalent foundations and infinity groupoids, providing a homotopical approach to construct higher category theories. Topological quantum computing and hypercomputation. In topological quantum computing, WITs are anyons, particles that exist in two-dimensional spaces, and their quantum states are determined by their braiding over time. Mathematical models include Yang-Baxter equations and mapping class groups of surfaces. The conspiracy angle here could involve the idea that such topological qubits could perform hypercomputation, computation beyond the limits of a Turing machine. The math gets incredibly complex, involving von Neumann algebras and the Jones polynomial in knot theory, which could theoretically be solved instantaneously using these topological qubits. Algorithmic information theory and the universe as a quantum computer. Algorithmic information theory, founded by mathematicians like Gregory Chaitin, deals with the complexity of algorithms and has applications in the theory of computation. In a computational universe hypothesis, one could argue that the universe itself is a quantum computer executing a complex algorithm based on principles from 8. Here you could employ notions like Kolmogorov complexity, which aims to measure the computational complexity of a string by finding the shortest effective binary program that produces the string as output. If someone were to crack the algorithmic complexity of the universe, they might be able to predict or even manipulate future events. The math here would likely involve highly complex formal systems, Gödel numbering, and perhaps even elements of quantum information theory, non-locality, entanglement, and global surveillance, quantum entanglement, and non-locality challenge our everyday understanding of the world. In quantum mechanics, entangled particles are described by a wave function that can't be factored individual parts, and this has been experimentally verified to produce correlations that can't be explained by classical physics inequalities. Conspiracy theories could speculate that intelligence agencies have secretly harnessed the power of quantum entanglement for surveillance, or even mind control, across vast distances. The mathematical formulations would include density matrices, EPR paradox equations, and hidden variable theories, arguably pushing into the territory of von Neumann algebras. Renormalization group flows in financial markets. Renormalization group Heitzelbrei. In quantum field theory describes how physical systems look at different scales and is key to resolving infinities in quantum electrodynamics. Advanced statistical mechanics also employ RG flows to analyze critical phenomena. In a conspiracy theory context, you could postulate that RG flow techniques are being utilized to analyze and perhaps manipulate financial markets in a way that is beyond the understanding of even the most advanced Wall Street quant. Their RG transformations would have to be adapted to financial modeling, employing complex stochastic differential equations and perhaps non-standard measure theory. Error-correcting codes in cosmic microwave background. Some researchers have half-jokingly suggested that if we find a sufficiently complex error-correcting code in the cosmic microwave background, that could be evidence we're living in a matrix-like simulation. Mathematically, you'd be looking at Beach codes, Reed-Solomon codes, and perhaps even lattices in high dimensions like the Leech lattice that have error-correcting capabilities. A conspiracy theory might suggest that governments are already aware of such cosmic codes and are deciphering them for advanced technological gains using lattice-based cryptography. Feynman path integrals in reality engineering, path integral formulation in quantum mechanics. Sums over all possible histories of a system. Some conspiracies might suggest that secret organizations have harnessed the ability to manipulate these paths to engineer reality itself. Mathematically, this would involve Wick rotations to transform the path integrals into a more easily computable form, and then perhaps using advanced Monte Carlo methods to perform the high-dimensional integrations. This could allow for the solving of quantum systems that are currently computationally intractable, thus leading to advanced predictive models or even manipulation of quantum states. Quantum error correcting codes and dimensional anomalies. In quantum computing, error correcting codes like the toric code or CSS codes are fundamental to mitigate the problem of decoherence. The math involves using Kitaev stabilizer formalism and sophisticated tensor network algorithms for optimal error recovery. In the speculative realm, what if these codes could be applied to correct errors in the very fabric of space-time? Such a concept might lean on the idea of anomalies in quantum field theory where classical symmetries break at the quantum level, of using cohomology classes to classify these anomalies. One could argue that a secretive organization has harnessed these principles to control dimensional gates or other exotic phenomena. A quantum topological order and subliminal control. As quantum topological order is a phase of matter that can't be described by local order parameters and exotic emergent excitations. Fractional quantum Hall states are a prime example.